Okay, hello everybody. Welcome to lecture number 20, which is about continuing on the theme of convergence of sequences. So we're in section 3.2 of the lecture notes. The theme is sequences and convergence. And last week we saw sort of the key theoretical ingredient here, which is the concept of convergence for sequences. So today we're going to see, I suppose, kind of our main theorem on this subject, which is the monotone convergence theorem. So just looking ahead, we've only got four scheduled lectures left. We're into the last 2 weeks of the semester. So basically this week, today and tomorrow, we'll be working on sections 3.2 and 3.3 of the lecture notes, which are of course available on the course calculus homepage. So today's theme really is the monotone convergence theorem, which you'll meet shortly if you haven't looked at it yet. And the theme for tomorrow is convergence of series. So essentially we'll see all of this in the next 2 days, but the distinction between a sequence and a series is that a sequence is just a list of numbers, but a series is a sum of infinitely many terms. So basically, essentially, the sum of all the terms in a sequence. So what we're going to do tomorrow is adapt our kind of machinery and conceptual, I suppose, concepts that we've developed for sequences to the case of infinite series, where there are some very interesting and, at least in my opinion, quite compelling reasons to want to be able to deal with them. And then next week, we have one more topic left in this general theme, and that's the idea of representing a function as a sort of infinite sum, not an infinite sum of numbers, but an infinite sum of powers of the variable x with respect to which the function is written. And those things are called power series representations. And they're an incredibly useful tool for actually dealing with functions and doing calculations with functions and evaluating functions that we can't evaluate directly. And that's something that we all sort of use all the time, in hidden ways, even if we're not really doing mathematics, that, this concept of being able to calculate values of things like trigonometric and exponential functions using power series. So really, we're kind of at the moment in this chapter, I suppose we're kind of concentrating on the sort of theoretical definitions and the concepts that we need, like the concept of convergence for a sequence, which are, I suppose, somewhat abstract things to get our hands on, and maybe not the most, maybe the reasons why we need these concepts might not be at the moment kind of completely clear, but I hope that will become a little bit more practical in the next couple of sections as we translate these ideas from the world of sequences to the business of series and also representations of functions. So basically we have 2 topics after today, which will each kind of take us one lecture, tomorrow for series, and next Wednesday we'll have a look at these power series representations of functions, just a first introduction to that, which is by itself, a huge subject that people spend their lives studying. So and then that will leave us Thursday's lecture next week for review and a little bit of exam preparation. So just on that note, I guess I should say something about it because it is getting nearer. So next Thursday we'll try to keep the lecture free of new content so that we'll be able to use it for talking about exam advice. And there is some exam advice already posted on the website, and as you know, the final section of each chapter of the lecture notes has a little bit dedicated to the exam advice on the corresponding question. So what I propose to do next Thursday is to basically use the time to have a look through some sample exam type questions on each of the 3 chapters. I'll also have some general advice for this year, but it doesn't differ so much from other years, despite all the differences this year in the way we've been able to engage with each other. So that's my plan for next Thursday. If there's anything in particular that anybody would like to include in that, please let me know in advance by email if you have a chance. And if we don't have time to go through an entire sort of set of sample questions next Thursday over the 3 chapters, I can add some supplementary video tutorials or whatever and put them on the website. So we will have a good chance to discuss what's involved in the exam paper, what I would expect somebody to write under the limitations that apply and the constraints that apply in an exam context. The exam obviously would be happening. Everybody would be in their home location, just as we are for lectures. And so the plan would be that the format would be basically similar to recent years, and there'll be 6 questions in all, 3 algebra questions and 3 calculus questions. Each of the calculus questions, the 3 of them would be based on the 3 sections, the 3 chapters of the lecture notes. And each of them will have 4 parts, which will carry the same weight for the 3 calculus questions. And so I guess the general sort of style and format will be similar to recent years. What's different this year, obviously, is that everyone will be at home and will have access to the lecture notes and to some, and access to sort of consult some materials and some resources. So that part's different. I hope it'll be helpful. But it means, for example, that you'll have access to the definitions and to anything that's in the lecture notes while working on the exam. And then the plan would be to create a scanned copy of your handwritten responses to the questions and upload them via Blackboard. So about those kind of technical details about the actual process, we will have further advice on that shortly. But I guess by the time the exam comes around, you'll be very used to this, since it is happening across the board, not just for this module. So yes, that's the plan, and more on that, I suppose, shortly, and in particular next Thursday. So just to repeat, if anybody has anything that they'd particularly like to include in next Thursday's review lecture, please do let me know, and I will do my best to include it. Again, if there's too much to include in one lecture, we'll create some additional resources and post them. Okay, anybody have a comment or question on any of that right now? Okay, so we're not at the moment, I think, under extreme time pressure, but we should get on with things at the same time. So we're talking about sequences, and let me just recall the key definitions from last week, just so that we're all on the same page. So this is basically recalling from last Thursday's lecture. So a sequence, I'm going to be a bit informal here, is an infinite list of numbers. Of real numbers. So, you know, the terms of the sequence are the numbers that are in it. They're called terms in this lingo. So we've got the first term A1, second term A2, third term A3, and so on. And the first term doesn't have to be called A1. It could start with A4 or go A4, A5, A6, whatever. But the point is that the terms in the sequence are indexed by usually by natural numbers, and they increase. So the first term doesn't have to be called A1. It could be called A0. It could be called A4. But the indices on the terms do increase as consecutive natural numbers as we roll out along the sequence. So an example of an infinite sequence, I mean, probably everybody's favorite sequence is the sequence of natural numbers that goes 1, 2, 3, 4, 5, 6, and so on. That's certainly an example of an infinite sequence. Another example of an infinite sequence, just to make the point that the terms don't all have to be distinct, you could have an infinite sequence whose terms are all 1. And that would be an example of an infinite sequence, certainly. You could have an infinite sequence whose terms, for example, are fractions starting with 1 over 1 and then going 1 over 2, 1 over 3, 1 over 4, and so on. That would be another example of an infinite sequence. So anything like that, basically an infinite list of numbers. Okay, and why do we care? Well, that hopefully will become more apparent as we proceed. But one thing that we do care about with sequences is this notion of a sequence having a limit. So let me just recall what that means. So the sequence, and very typical notation for sequences is to write like sort of something to represent the nth term in round brackets to indicate that we care about the order of the sequence. Actually, that's the point. I should just recall it, that, you know, we do care with a sequence. It's not like a set in the sense that we do care which is the first entry, which is the second one, which is the third one, which is the fourth one, and so on. So if you take the first sequence there, that goes 1, 2, 3, 4, 5, 6. If you swap the order of the first two terms and write the sequence 2, 1, 3, 4, 5, 6, that's considered to be a different sequence. Okay, so the sequence is not just the set of all the terms in the sequence, the order matters as well. So, you know, the sequence that goes 1, 2, 3, 4, 5, 6, and so on is a different sequence from the one that goes 2, 1, 3, 4, 5, 6, and so on. Okay, we do care about the order in which the terms are listed. It doesn't matter which one is the first one, which one is the second one, and so on. Okay, so the sequence AN converges to the limit L. If you're thinking about this definition, and I suppose you're arguably, there are some benefits to this open book exam business, maybe, in that you don't have to memorize this definition, as you might have had to do, at least for the exam in previous years. You'll have access to it, but you do have to be able to interpret it and to be able to kind of make sense of it, I suppose, possibly within a time-constrained environment. So what it means to say that a sequence converges, one thing to remember when you're thinking about trying to describe this is if you're going to say that a sequence converges, you have to have a number in mind that it converges to. And what it basically means, in very rough description, is that the terms of the sequence are clustering around this number L very closely as you move out through the sequence. But more precisely what it means is that for any real number epsilon, so epsilon is a Greek letter that looks like that. This is epsilon, and traditionally it's used, and conventionally, maybe more than traditionally, it's used to denote some very, very small quantity in mathematics. If for any real number epsilon, there is a value n beyond which all terms of the sequence. And what I mean by all terms of the sequence beyond, like this one denoted by capital N, beyond which all terms of the sequence, that means all AN for which N is greater than this capital N are within epsilon of L. Okay, so it's not just that the terms get nearer to L, it's that no matter how near you want to be to L, you can reach a stage by traveling far out along the sequence beyond which every term, every single one from that point onwards is within epsilon of L. And no matter how small you choose epsilon to be, you can reach a stage where everything in the sequence would be sandwiched between L minus epsilon and L plus epsilon. And I suppose the picture that accompanies this is it's sort of like this. You've got some limit L in mind. So this is like the horizontal line y equals L. And we're saying that no matter, and you know, you've got an x-axis and a y-axis somehow in the picture. So the red line there is the line y equals L. Along the x-axis, along the horizontal axis, you've got points labeling all the natural numbers, and sort of imagine that there's, you know, the right-hand side of this picture is somehow like far out along the positive direction of the x-axis. And what you're saying is that no matter how, if your sequence converges to L, no matter how narrow a sleeve you pick around L, so these pink lines are supposed to be like really close to L, just one on each side of it. One represents L minus epsilon, and the other one L plus epsilon. And we're saying that no matter how narrow you take that band to be, you can travel far out enough, and beyond that point, all the terms in the sequence, which are represented by these green dots, so maybe there's A1, A2, A3, and so on. That, you know, they can do anything at the start, but if the sequence converges to L, then you have to sort of hit a point where they're all sort of clustered around L very finely. And the meaning of very finely is that no matter how finely, how narrowly, how nearly you want them to be clustered around L, they are that close to L if you travel far out enough. Okay, so that's the concept of convergence. So basically, like kind of, you know, informally, it means that, yeah, the terms of the sequence are clustering around L, they're getting near to L, they're converging to L. The word converging, maybe even in its kind of ordinary usage, sort of captures that. So with these examples up here, the sequence whose terms are all 1 is definitely converging to 1. You know, its terms are all actually equal to 1. It couldn't be converging any better than that. So yes, there's certainly, no matter how narrow a band you draw around 1, all the terms of that sequence are within it. The last one here, this one's converging to 0. Because certainly we can probably agree that if you look at, you know, 1/5, 1/6, 1/7, 1/8, 1/9, 1/1,000,000, those things are getting close to 0. And no matter how narrow a band you draw around 0, a kind of like sleeve around 0, like this pink sleeve around L in the picture, you can, by choosing the denominator here big enough, you can reach a point beyond which all terms of that sequence are within that sort of tolerance of 0. Okay, so that's the concept of convergence for a sequence. And does anybody want to ask anything about that right now? I suppose it is a concept that's worth sort of spending a bit of time getting used to if you can, and kind of, you know, getting a sort of sense for what it says, which is not necessarily something that you achieve just by kind of reading the words. It's, you know, you kind of have to try out some examples and maybe draw this picture a few times yourself in your own sort of preferred appearance. So yeah, it's a definition that you'll meet sort of again and again if you persist with mathematics. Okay, so that's what we talked about last week, basically on Thursday. Okay, a couple of extra properties that sequences can have that we need to give a little bit of attention to. So we have the concept of a bounded sequence, and this means, I think, probably what you'd guess it means, which is that a sequence is bounded if its terms are contained within some range. They don't fly off to infinity, either plus infinity or minus infinity. Okay, that's what it means, and that's what I would say it would mean. That's what I'd say it means if we were having a conversation face to face. Of course, that's not really kind of precise if you're trying to convey it in writing. So a sequence is bounded if the set of its terms, if you consider them just as a subset of the real numbers rather than as an ordered list, is a bounded set. Okay, so we talked about boundedness in the context of sets. A set of numbers is bounded if when you write all the points that represent its elements on the number line, they don't spread over the entire number line, but they're contained within some interval. And it's the same thing here. And equally, of course, you can have the idea of a sequence that's bounded above or bounded below. So a sequence is bounded above if there's a real number written there as capital M with the property that no term of the sequence exceeds this capital M. So basically, you know, when you draw the picture of the sequence as kind of a graph like that with, you know, the natural numbers labeling the horizontal axis and the terms of the sequence represented by y coordinates. So a sequence is bounded above if there's some kind of horizontal line that's like a roof for the whole picture, that there's no point of the sequence that goes above it. And similarly, bounded below would be the similar picture, but we have a floor rather than a roof for the entire picture. Okay, so the sequence is bounded above or bounded below if it's got an upper bound or a lower bound. And the sequence is just referred to as being bounded, exactly as we do for sets if it's bounded both above and below. Okay, so that's a property that sequences may or may not have. And so for a few examples, if you look at the sequence, and so yeah, here again, I suppose part of the thing here is to recognize the notation that's been flying around. So the sequence, this thing, this n with round brackets, and referred to as a sequence, what that means is just the sequence whose nth term is the natural number n. So it's the sequence 1, 2, 3, 4, 5, perfectly good sequence, not convergent, but you know, lots of other nice properties. So that sequence I claim is bounded below, and the reason for that is yes, if you look at all the numbers that are in that sequence, 1, 2, 3, 4, 5, 6, 7, there's a point below which they don't go. None of them, for example, is less than 0. None of them is less than 1 indeed. So that's a sequence that's bounded below because there's no term in that sequence that crosses below, for instance, 0 or below 1. Okay, it's not bounded above because the terms of the sequence increase without bound. Okay, no matter how big a number you choose, there are terms of the sequence that are bigger than it. The number eventually reaches 10 million, 20 million, whatever, any huge number that you can pick. The terms of the sequence get bigger than it, but it is bounded below because, for example, it doesn't have any numbers that's less than 1. Okay, if you look at the sequence sine n, this is a kind of maybe a nice example. You know, its terms, this means sine of 1, sine of 2, sine of 3, etc. And, you know, again here, I'll take the opportunity again to remind everyone about how, you know, how to think about these numbers, sine 1, sine 2, and so on. Sine of 1 is the number that you get if you start at the point 1, 0, the sort of rightmost point there in the unit circle, travel anti-clockwise around the circumference of the unit circle, a distance of 1, so distance the same as the radius. And sine of 1, the sine of 1 is the y-coordinate of the point that you reach by doing that. The sine of 2 is the y-coordinate of the point that you reach by traveling a distance of 2, where 1 is the radius length, around the circumference from 1, 0 in the counterclockwise direction. Stop after you've traveled the distance of 2, and the y-coordinate of where you are is the sine of the number 2. Okay, and so on for sine of anything else. So the sine of 1, sine of 2, sine of 3, great. We can sort of understand them in that geometric way. We don't know the values of these numbers, they're decimals, but we can't say, even without knowing their values, that they're definitely no greater than, none of them can be greater than 1, and none of them can be less than minus 1, because when you travel around the unit circle, you never hit a point that has a coordinate that's outside the range, minus 1 to 1. So I think it's a nice example to kind of illustrate the concept of boundedness, this sequence of sines of the natural numbers, or cosines. If you prefer cosine, you can take that. It does the same trick. We can say for sure the sequence is bounded. None of its terms are less than minus 1 or greater than 1. And we can't say a whole lot more about it unless we want to do a lot of work, but we can certainly say with certainty that it is bounded. Its terms are all in the range minus 1 to 1, and they can be really anything within that range, but they are within that range. Okay, so that's an example of a bounded sequence. The sequence sine of anything is bounded below by minus 1, for instance, and above by 1. Okay, so that's the idea of a bounded sequence. And okay, why do we care about bounded sequences? A couple of reasons. One of them is that certainly, I guess this is intuitively probably not too surprising, that if a sequence is convergent, and convergence is what we really care about with sequences, but if a sequence is convergent, it must be bounded. And quite often you can be in a situation where you've got some sequence in mind that arises maybe from some function that you're interested in or something like that, and you maybe want to know, is it convergent? And one of the, that might not always be very easy to show. You know, you might not have a very tight handle on what exactly the terms are. And, you know, you have a definition for convergence, which is sometimes very useful, but maybe it doesn't exactly maybe it's not easy to apply it to whatever your sequence is in the form that you have it in. So it might not be easy to decide if a sequence is convergent or not. But one prerequisite for being convergent is that it must be bounded. And that means, for example, if you have some sequence in mind and you can see that it's not bounded, then it has no chance of being convergent. So you can sort of rule out straight away any possibility of it being convergent. Okay, why is this true? Why must it be true that if a sequence is convergent, it must be bounded? Well, this is actually plausible, I suppose, but also it's maybe a good exercise in sort of writing down a proof involving reasoning with these definitions that apply to sequences and how we can use them. So let me try to say something about this proof without just reading it from the slide, and also let me try to add a picture that hopefully won't totally destroy the readability of the whole thing. So, okay, so the assertion is that if a sequence is convergent, it must be bounded. Okay, so let's give ourselves a sequence which is convergent and try to persuade ourselves that, based on what we know about convergence, that it must also have this property of being bounded. So the picture, I suppose, for any sequence is we've got the natural numbers 1, 2, 3, and so on. We'll imagine that our picture here is of a sort of a very large region of the real numbers. So we put a few dots to indicate that this number line stretches out. And where we are over here is kind of far out along the number line. Okay, we're saying that our sequence is convergent. That's a hypothesis of this theorem. So there's some L, which is a limit, which is the limit of our sequence. So let's say that let's say that our y-axis is here. This is the point with coordinates 0, 0. And so we've got the horizontal line through L. And as we draw the points of our sequence, they eventually get sort of clustered around L. Okay, so what we know, because the sequence is convergent, we can say that for any epsilon that we pick, no matter how small it is, all the terms of the sequence eventually fit into the sleeve of radius epsilon around L. So let's just take L minus 1 and L plus 1, which, depending on the context, maybe you're not particularly close to L, but that doesn't matter so much, because the definition of convergence tells us that at some point the sequence is converging to L. And so the terms of the sequence are represented by dots whose y coordinates are the values of the terms and whose x coordinates are 1, 2, 3, etc., that index the terms. So there is a stage beyond which every term of the sequence is in this sleeve of radius 1 or of width 2 between L minus 1 and L plus 1, kind of like a sleeve of radius 1 around L. Okay, so the fact that the sequence converges to L tells us that in particular there's some n, maybe here, beyond which every term of the sequence is between L minus 1 and L plus 1, which means between those two blue lines. So as soon as we pass n heading out in the increasing direction, every term of our sequence is in that blue sleeve. Okay, we don't know exactly how they go. We do know that we could get them into an even narrower sleeve around the red line by traveling further out, but we don't really need that, because what this is really saying is that from that point n, capital N onwards, the terms of the sequence after that stage are between those two blue lines. So they're certainly bounded. L minus 1 is a lower bound for all the terms beyond this stage, and L plus 1 is an upper bound for all the terms beyond this stage. So, the picture of an unbounded sequence in this form would be something where the pink dots are just flying off the page, infinitely far above and below, above or below, at least one of above and below. Okay, so if the pink dots are sort of contained between two horizontal lines like that, that means the sequence is bounded. So we're saying that it's bounded from this point onwards. Anyway, we still have to worry about the sort of previous bunch of terms, but the point about the previous bunch of terms, so from 1, 2, 3 up as far as, I don't know, let's say n, I suppose, that's a finite set. So the terms of the sequence from 1 up to n, so n is some fixed number, like it could be 100 or 10,000 or whatever, but it's a fixed number. So before the nth stage, to the left of this part of the picture that's filled in, we only have finitely many terms. So a set with only finitely many elements in it, finitely many real numbers, has to be bounded. It can't fail to be. Like, you can list its elements in order and you get to the end of that exercise. So amongst the first lot of elements before we hit n, there's a greatest element, m1, amongst this lot. So maybe it's here somewhere. So I've called it M1 here in the note. So somewhere amongst the first lot, there's a greatest element. There's only a finite number of them before we hit this point beyond which they're all bounded. And there's a least one as well in that first finite range. So maybe it's M1. So maybe it's there somewhere. So basically, the first part of the blue lines are not really relevant in the first part of the picture before this pink dashed line, because we don't know for that first initial part whether the terms of the sequence are all contained in the blue sleeve or not. We know that they are to the right of the purple dashed line, and that's what the fact that the sequence is convergent tells us. So the part to the left is finite. There are only finitely many terms there, and amongst those finitely many terms, there's the greatest one and there's the lowest one, M1. So every term in the sequence, if it's to the left of the pink dashed line, is less than or equal to this M1. And if it's to the right of the purple dashed line, it's below the upper blue line. Okay. So basically, whichever one is higher, the M1 or the upper blue line, is an upper bound for the entire sequence. So we can say that the sequence is bounded above either by this M1, which is the maximum of the first finite lot of terms, or by this L+1, which is this blue line. Okay, so the sequence is certainly bounded above, and we can say the sequence is bounded below as well. So again, I've drawn the little M1 here, which is like the minimum element of the first finite collection of terms. I've drawn it so that it's above the blue line L-1. It could be below, we don't know where it is. But the point is, either the lower blue line or this minimum of the first n elements is a lower bound for all the terms in the sequence. Whichever one of them is basically lower is a lower bound for the entire sequence. So yeah, so basically if we write M to be the maximum of L+1, which is an upper bound for the tail on the right, or the maximum of the first few elements before you get into that regime, that M would be an upper bound for the entire sequence, and similarly for a lower bound. Okay, so if a sequence is convergent, it must be bounded. And so I think this is something that certainly is worth remembering and worth having in your mind whenever you're thinking about convergence. But I think this proof is also worth giving a little bit of attention to when you have an opportunity, because it does kind of capture how we can use the definition of convergence for some reasoning with sequences. So our hypothesis here is the sequence is convergent. And again, when you're thinking about how to translate that useful fact into something that you can reason with, remind yourself it's convergent. That means it has a limit, and that limit L is something that I can work with. So, okay, that means if I draw a picture with L in it, I don't know the value of L, but it doesn't matter. L could be 2 or 3 or whatever. It's some fixed number. I can draw a sleeve around L of whatever width I want. I've chosen a sleeve of width 2, so of radius 1. And I know that I'll reach a stage in my sequence beyond which everything is within that sleeve. And that kind of means really, this pink vertical line here is sort of divides the problem into two parts. The part to the right of it is the problematic part in a sense, because it's the infinite part. Okay? But the part on the right is dealt with by the definition of convergence. We know that part of the sequence is bounded because everything there is between L-1 and L+1. The part on the left, we don't know anything about where the terms are, but it's a finite set. So for that reason, we know that it's bounded. Okay, so basically the sequence is sort of, it's composed of two parts, a finite part that's bounded because it's finite, and an infinite part that's bounded because the sequence is convergent. Okay, and putting that all together, we find that the sequence is indeed bounded. Okay, so that's the strategy. And of course, choosing the L-1 and L+1 here is a completely arbitrary choice. You could choose L-2 and L+2 or L- whatever you want. The point is you get into that bounded regime because of the concept of convergence once you've traveled far enough out. We don't know how far enough out is, but it's finitely far. So everything to the left of that is in a finite set. Okay, so every convergent sequence is bounded. That is good because it relates to important properties of sequences. And of course, now we might ask, well, what about the opposite of that? Is it true that every bounded sequence must be convergent? So I'm going to take a break for a second to let you think about that for a bit. While we digest some of these concepts. Oops, what happened there? Okay. Right, so why is my slides frozen? Okay, so I'm going to stop the recording for a second while Okay, so it is not true that every bounded sequence is convergent. And, I guess that might not be obvious at the beginning when you think about it, but it's not hard to write down examples of sequences that are bounded but not convergent. So for example, if you take the sequence whose terms just alternate between 0 and 1, 0, 1, 0, 1, 0, 1, 0, 1, that sequence is certainly bounded. It only has two distinct terms. So there's nothing in it that's greater than 1 and nothing in it that's less than 0. But it's certainly not convergent because it just keeps oscillating between 0 and 1, no matter how far out you travel. So there's no sleeve that you can write around any number, no narrow sleeve you can put around any number that the terms of the sequence will all eventually get in there, unless it's quite a wide sleeve. So that's an example of a sequence that is bounded, but is not convergent. So unfortunately, the converse of this theorem is not true. It's not true that bounded sequences and convergent sequences are the same thing, but it is true that every convergent sequence must be bounded. Okay, but we can get sort of a partial converse to the theorem on the last slide by adding a few more conditions. So next thing to give our attention to, the concept of increasing and decreasing sequences. So this again kind of means what you would think it would mean. So a sequence is increasing if, as you read its terms, first, second, third, fourth, fifth term, and so on, their values increase. They don't decrease. Okay, so a sequence is called increasing if the nth term is always less than or equal to the n plus first term. Okay, so examples of this. An example of an increasing sequence. So an increasing sequence is where every term is at most equal to the next one, where you never have a decrease going from one term to the next. So obviously if you take, for example, the sequence 1, 2, 3, 4, 5, 6 of all natural numbers, that's certainly increasing. The terms increase as you read them out from the first onwards. Another example would be, just to make the point, I guess, that, in the definition here we say less than or equal to. So it's okay for two consecutive terms to be equal to each other, but it's not okay for one term to be greater than the next one. So you could have, for example, the sequence which has 1, 1, 2, 2, 3, 3, 4, 4, that would also qualify as being increasing in this, according to this definition. Okay. And another one, maybe just to have a convergent example, if you take the sequence whose terms are -1, -1 half, -1 third, -1 quarter, and so on. That's an example of an increasing sequence as well. Its terms are, they start at -1 and they increase gradually, or well, not that gradually, but towards 0. And that's an example of an increasing sequence that is bounded above by 0 and that actually converges to 0. Okay, so those are examples of increasing sequences. Okay, and here this is just kind of a bit of fussing that I'm going to inflict on you in case you encounter it anywhere if you're reading somewhere else. It's not something that we need to worry about too much, but there's this distinction between increasing and strictly increasing. So a sequence is strictly increasing if each term is strictly less than the next one, and that's just a language that, increasing terms can have, an increasing sequence can have consecutive terms equal to each other, but a strictly increasing sequence can't. So this one would be an example of an increasing sequence, but not strictly increasing. The other two are strictly increasing. Increasing, that's completely illegible. Okay, so and similarly we have the concept of decreasing and strictly decreasing. So a sequence is decreasing if every term is greater or equal to the next one, and strictly decreasing if that inequality is strict. So an example there, I suppose, would be if we take the let's take minus the natural numbers, -1, -2, -3, and so on. That's a decreasing sequence. Okay, its terms are decreasing as we read them out. So most sequences are neither decreasing nor increasing, in the sense that if you write down if you somehow generate a sequence randomly, it won't be either increasing or decreasing. It'll have some places where it increases and some places where it decreases. So these are special properties for a sequence to have. And a bit of another word for our vocabulary, a sequence is called monotonic if it's either increasing or decreasing. So I suppose the reason for introducing this word to the dictionary is that it's kind of handy to have a word that covers both increasing and decreasing, because the theories that describes increasing sequences is pretty much the same as the theory for decreasing sequences. So people use the term monotonic to describe the phenomenon where a sequence is either increasing or decreasing, but they don't necessarily care which. Okay, so a sequence is monotonic if it's one of those things. And so an example of a non-monotonic sequence monotonic sequence would be something like this. Let's say if we go 1, 3, 2, 4. So we take the first 2 odds, then the first 2 evens, then the next 2 odds, then the next 2 evens, and so on. Okay, so that's a sequence. It's not too bad in terms of its, in terms of the pattern. But it increases from 1 to 3, then it decreases from 3 to 2, then it increases again, then it decreases again. Sorry, it increases, then decreases, then increases, then increases, then increases again, then decreases, then increases. So that's an example of a sequence that's neither increasing nor decreasing because it doesn't have uniform behavior all along. Okay, it has sometimes it increases from one term to the next, sometimes it decreases. So it just doesn't fit into any of these patterns. So yes, to say that a sequence is increasing means it has to have this kind of uniform behavior right along its entire definition. It can't ever, even in one place, decrease from one term to the next. So if you generate a sequence according to some random process, it will probably have both increases and decreases. Note there, just to annoy us, there are some authors who use these terms a bit differently. So, for example, who would call increasing what we've called strictly increasing, and call what we've called increasing they call non-decreasing, which means that, you can't have a decrease, but you can stay constant from one term to the next. That note, please ignore it unless you encounter something in your reading where it's necessary. It won't affect us in our discussion within the lecture notes, but it's something that if you're reading elsewhere, you might have to grapple with, which is it's a bit annoying that we can't agree on terms, but that is something that we have to live with. Okay, a few examples. So an increasing sequence will always be bounded below, for example, by its first term, because no term in an increasing sequence can ever be less than the first one. So that's a remark. An increasing sequence is always bounded below. It need not be bounded above. So for example, the natural numbers is an increasing sequence, which is not bounded above. Its terms grow to infinity. A bounded sequence need not be monotonic. For example, the sequence can be bounded, as I was saying, and its terms can alternate between more than one value. A convergent sequence need not be monotonic. So for example, if we take the sequence whose terms are basically fractions 1, 1/2, 1/3, 1/4, but with alternating signs so that every second one is negative and positive, that sequence converges to 0, but it is not monotonic. It is, of course, bounded. So, and a monotonic sequence need not be convergent. So the relationships between convergent, monotonic, and bounded, I guess, is what we're trying to kind of unravel. And we know that a convergent sequence must be bounded. And we know that a monotonic sequence might be bounded, might be convergent, but might not be either of those things. So the assertion is that if a sequence has the properties both of being bounded and monotonic, then it is convergent. Okay, and those, of course, those are strong properties for a sequence to have. Being monotonic, in particular, is a very strong property for a sequence to have, because it means you can't have places where it increases and places where it decreases. It can only do one of those things throughout its entire infinite sort of list of elements. On the other hand, I guess it's not surprising to suggest that although monotonicity is a very strong property for a sequence to have, it is a sequence that does tend to, it is a property that crops up in examples that are of interest. So for example, people use sequences in topology and in number theory and in analysis, and quite often there are good reasons why sequences that turn up there are monotonic, and that means that this theorem can apply to them, which is the monotone convergence theorem. So this is our big theorem on this for this section. It's actually kind of our last big theorem as well of the course. So it says that if a sequence is monotonic and bounded, then it is convergent. Okay, so we're going to prove this. And we have all the ingredients to prove it. I think for me, the tricky thing in this proof is just to figure out how to factor in the concept of convergence when you're trying to prove it. So we're trying to prove that if a sequence is monotonic and bounded, we give names. This is monotonic, there's a typo there. We give names AN, A1, A2, etc. to the terms of the sequence, and we want to show that we assume that it's monotonic and that it's bounded, and we want to show that it is convergent, okay, that it converges to some limit. Okay, and because we have a hypothesis that it's monotonic, that means it's either increasing or decreasing. We have to, in principle, sort of deal with both of those, but let's give ourselves one of them, and the proof for the other one will go the same way. So let us assume that our sequence, that the way it's monotonic is that it's increasing. Okay, so that means that AN is less than or equal to AN plus 1 for all n, that its behavior is to increase from one term to the next. Okay, and if you want to give yourself a task to understand this proof, do the corresponding proof for the decreasing version, and you'll see that everything works the same way. Okay, so we have to prove that the sequence, if it's increasing and bounded, must be convergent. And I guess like the picture here is we've got a sequence. It's increasing. So we've got 1, 2, 3, 4, etc. here on the horizontal axis, and so on. It travels onwards. And we've got terms of our sequence. And what we know from the fact that the sequence is increasing means that the dot that represents term A1 is lower or no higher than the dot that represents A2. So the kind of behavior has to be like this. No dot can be lower than any dot to its left. So maybe it goes like this, maybe it goes like this, and so on. Maybe it has kind of bigger increases at some places and smaller ones at other places. But the trend has to be upwards. There can be no downward steps as we travel from left to right through the dots that describe this sequence. And also, this green line on top here is kind of a roof for the whole picture. It's an upper bound. So the dots cannot ever cross that green line, and they can't ever go downwards. As we travel from left to right through the picture, the trend and the dots has to be always upwards. They can stay level for a step or two, but they can never go down. Okay, so and that's somehow is basically how the picture has to look. Okay, so it has to have that general shape. Okay, so to arrive at a conclusion that the sequence is convergent, we have to be able to say, well, there's some number which, with the property, that no matter how narrow a sleeve we draw around that number, all the terms of the sequence eventually get in there. And I think the hard thing about this proof for me is to figure out how you're going to get that into the picture. We don't have a candidate for what the limit might be really at the moment. We just have a sequence that's increasing and bounded. So the key step here, and once you kind of see the step, the rest of it flows kind of from the basic machinery, is how to produce a candidate for a limit for this sequence. Okay, so the set of terms of the sequence is a bounded subset of the real numbers. Okay, that means the set of its terms is contained within like a pair of green lines as in that picture. It's a bounded subset, and the axiom of completeness tells us then that it has a least upper bound or a supremum. Okay, so we have to invoke the axiom of completeness to establish or to give ourselves a supremum, and we're going to give the name L for the supremum. The notation is supposed to suggest limit, and certainly we will see that the sequence does converge to L. Okay, so here's the picture, and it's essentially the same picture, but instead of taking any old upper bound like that green one, we're going to take the supremum of the set of terms in our sequence, which we know exists because of the axiom of completeness. Okay, and the claim is that the terms of the sequence must be converging to L. Okay, how can we actually justify this? Well, if we choose a very small epsilon, there's no terms above L because L is an upper bound for the sequence. So it's below L we need to worry about. So if we choose a very small epsilon and draw the line L minus epsilon just below the line L there, and remember again, there's nothing in the picture that's above the line L because L is an upper bound for our sequence. So it's the lower side we have to think about. L minus epsilon is not an upper bound for our sequence, for the terms of our sequence, because L is the least upper bound, it's the supremum. And this means there's some n with the property that every term beyond the nth term is at least equal to, sorry, there's some n with the property that the nth term, an, is greater than L minus epsilon. How do we know that? Because L minus epsilon is not an upper bound for our sequence. L was the least upper bound, and L minus epsilon is less than L. So L minus epsilon is less than an, but moreover, the sequence is increasing. So if L minus epsilon is less than an, then it's also less than every subsequent term after an. Okay. L, which is the pink line, is an upper bound for the sequence. So we're saying that all terms of our sequence from n onwards, from the nth term onwards, are squeezed into that region between L minus epsilon and L. And no matter how small epsilon we choose, we can still achieve that because L minus epsilon won't be an upper bound for the terms of our sequence. So basically what we're saying is that if a sequence is increasing and bounded above, then its terms have a supremum, and the terms of the sequence are converging to that supremum. So no matter how small an epsilon we take, there's a point in our sequence beyond which all terms are in that little band between L minus epsilon and L, and that's exactly what it means for the sequence to converge to L. Okay, so that's the monotone convergence theorem. It's kind of our main theorem at the moment about properties that make a sequence convergent, and it's something that's worth thinking thinking about it a little bit. It is useful in very many applications, in very many contexts. Okay, but what we're going to do next, tomorrow, is that's section 3.2 about convergence of sequences. Tomorrow we're going to look at something a little bit more, maybe sort of slightly more feet on the ground, which is infinite sums, and how we can apply this theory about convergence of sequences to the problem of figuring out when the terms of an infinite sequence can be added together to give some kind of numerical value. And that's something that is very useful in practical applications as well as in theoretical developments. So a couple of learning outcomes there for this section. We'll return to all of that at the end of the chapter. That's it for section 3.2, and that's it for today. Thank you very much to everyone who's joined us for the recording. So I'll stop that now.